In this video, again, I want to look at equations of this sort and see what sort of polar graphs it gives me. I'm going to do it just like the last one, although in this case, this is case 2, where e equals 1. Okay, so I'm looking at this thing with e equals 1 here. Again, I'm going to start by drawing just the graph of the denominator and then looking at the reciprocal here. So in blue, this looks like an amplitude 1 cosine curve shifted up 1. So it goes up as high as 2 here, and it goes down as low as 0. It's this cosine curve that just does something. That's about the ugliest looking cosine curve I ever drew. Maybe not. You've seen a lot of ugly cosine curves from me. Here we go. That's 2 pi right there. Notice at pi, this actually hits the theta axis. This is theta now. This is r. And I'm just doing this so I get an idea of what the relationship between theta and r is. As theta is getting bigger, r starts off big, goes down to 0, comes back up. Okay. Now, more to what I want to look at is I don't want this graph, I want the reciprocal of that, right? Because I want this stuff in the denominator. So in red here, we will draw the graph of this one now. So when this is 2, the reciprocal's down here at a half, right? When this is 0, oops, sorry, let's go right here. When this is 1, the reciprocal is 1. And when this is 0, the reciprocal is infinity. So there's actually a vertical asymptote at this point. And this heads on up to infinity, and then it comes back down again just in the same method. What does the A do? Well, the A just scales it up or down, where this was at a half right here. So, sorry, I was going to grab a different color here. Grab some green. Right? When this is at a half, then A times a half would be A times a half, whatever. It scales it up. So the green graph is just a scaled up or down version of the red one. If A is less than 1, of course, this would scale it down, and the green graph would be underneath there. And if it's negative, then it would all be upside down. But the idea is still the same in that you start off with some value, you head out to infinity, and then you come back again. Okay. Now, let's draw this in polar coordinates. So this is the xy plane, and I'm thinking of theta as an angle and r as a distance. So what's happening here? We start off with theta equals 0, looking at this direction. We start off at some distance here, which is a times a half, right? It's a over 2. Then what happens? As we move further and further away, this graph gets farther and farther away, and in fact, these get bigger and bigger and bigger and bigger, and by the time you're looking in the direction of pi, this is infinitely long, so this graph never comes around and hits there. It just keeps headed out here. And likewise then, as I come back in here, it's really, really big, but getting smaller and smaller, and this comes in like that. So these are getting bigger as I'm going in that direction, or smaller as I'm coming in, right, that way. So start off at a over 2, get farther and farther away as we turn, out to infinity here, in this direction, and then coming back in again. It turns out that this is a parabola. And we'll prove that this does satisfy the equation of a parabola, so that that curve on the outside there is a parabola. Next, we want to look at e bigger than 1.